So in this video we look at more antiderivatives and differential equations. Okay. One thing we've hinted at in previous videos is a very important result. So we have a very important result that any two antiderivatives of the same function little f of x, differ only by a constant. Okay, this is a very important result. And it goes along with just the shorthand of this, that antiderivatives are not unique. Okay, there's a whole bunch of antiderivatives to a single function. Okay, so here's the key to this result. Let's say that you're given a function little f of x. Let's say that you're given this function. Okay, let's assume that you know that big F1 and big F2, let's assume that you have two antiderivatives of f. Assume F1 and F2 are antiderivatives of the function little f of x. Then what you know from those being antiderivatives is that the derivative of the first function f is equal to little f of x. And you also know that the derivative of the second antiderivative function that you found is also equal to little f of x, the given function. So both of these are true. If both of these are true, then you know that when you subtract them, if you subtract these two derivatives, that since both derivatives were equal to f of x, this one was equal to f, this one was also equal to f, that f minus f is equal to 0. So we know that the derivative of these two functions subtracted from each other is equal to 0. But by properties of the derivative, we know that the derivative could be written of the difference of two derivatives could be the difference of these two functions. That's a property of the derivative. And if the derivative of a function is equal to 0, that meant that the function that you took the derivative of had to be equal to a constant. The derivative of a constant is equal to 0. And this will tell you that f1 is equal to f2 of x plus a constant. This result says that if you have two functions that you know are antiderivatives of the same function, then they have to differ by a constant. Okay? This result is very important because it tells you that if you know any antiderivative, you know all the antiderivatives of a function. Okay, so let's take a look here. Okay, let's look and see how this could get phrased as a question. Okay, so example. Okay, example. Let's say that you know that the derivative with respect to x of sine of 2x, the derivative of sine is cosine, the derivative of the inside function is 2. So this is what we know. Okay, this is a known. Okay, we can rephrase this statement as sine of 2x is an antiderivative of the function f of little f of x is equal to 2 cosine of 2x. Okay, this function sine of 2x is an antiderivative of 2 cosine of 2x. But we also know that since this is an antiderivative, we also know that Any other function, g of x, well, let me call it sine of 2x plus any constant is also an antiderivative of 2 cosine of 2x. Right? Finding the particular constant is something that is left up to differential equation style problems that we'll look at in the next video. So here what we can say is that this f2 is the most general antiderivative of 2 cosine of 2x. Okay, so here are a series of antiderivatives that you should be familiar with. Okay, what we're seeing in this table are some functions and their antiderivatives that we should just be familiar with. If you have a function equal to 0, the antiderivative will be any constant. If you have a function f of x is equal to 1, then you know that one of the antiderivatives of 1 is equal to x. The derivative of x is equal to 1. But once you know that one antiderivative, if you just add any constant onto it, then that will also be an antiderivative of 1. Okay. We also have the power rule for antiderivatives, that if you have the function x to the a, that the antiderivative, like for example, if you have the function x cubed, then the antiderivative will be x to the 4th divided by 4 plus any constant. X to the 4th over 4 plus any constant is the most general antiderivative of x cubed. And what you see in the table is a variety of other antiderivatives. Okay. Looking at this one right here, here is our exponential function problem. What we know, which you may have known in the past, from the past, is that the derivative with respect to x of a to the x is a to the x multiplied by the natural logarithm of a. Okay? But what if you were asked a new question? What could you take the derivative of to give you a to the x? What could you take the derivative of to give you a to the x? And what we can see is that if we just reverse this, divide both sides by the natural logarithm of a, that when you divide both sides by the natural logarithm of a, you'll get a to the x. Because 1 over natural logarithm of a was a constant, it can go inside of the antiderivative. And here now we have a new equation that says that the derivative of a to the x over logarithm of a is equal to a to the x. And that tells us that a to the x divided by natural logarithm of a is the antiderivative and antiderivative of a to the x. And because you know this one antiderivative of a to the x, you can add any constant onto it, and that will also be an antiderivative. Okay? So there is a little bit more on a key result, that how the constants come into play with the most general antiderivative. Finding that constant is the subject of the next video on differential equations.